Assalamualaikum dan salam sejahtera pada semua. Hari ini kita teruskan chapter 4 untuk khusus KM 4362 Finite Element Method dalam topik Trusses. Okay. 4.1 the introduction. So before kita pergi jauh, Trusses, untuk menyelesaikan permasalahan Trusses dalam finite element secara analytical, secara calculation, we need to know the assumption that we need to understand, which is the first one. The bar is geometric straight, right? You can see from here the bar is geometrically straight. The second one, the method obey the Hooke's law, okay, F equal to Kx. And then the third one is force are applied only at the end of the bar, okay, the force will be applied at the end of the bar, not at the middle of the bar, for example, okay. And then the lastly is the bar support axial load only. It means that it just applied for the axial load only. For bending, torsion and shear are not transmitted to the element in the trusses. So that is the difference between trusses and also a beam that will be discussed for the next chapter. Okay. Okay, this is how we looks like our beam, our trusses. So from here we can see this is our node. We have node 1, node 2, node 3, node 4, node 5, node 6, node 7 and node 8. And for every node we have our degree of freedom. So from here, one node we have a 2 degree of freedom. For total of that, so we have our 18 of degree of freedom. Okay, so I think this is quite similar with the previous lesson, which is the 2D, two-dimensional of the finite element. So from here kita ada juga ada axial force acting on the end of the on the bar. Okay. So we go through. For every truss element is the direct tension or compression in the truss is required to all nodes and direction are applied only at the joint, and that all members are connected together at the end by the frictionless pin joint. Alright, so it's very straightforward. So we go through the second section, which is the plane trusses. Okay. So from here, the point that we need to highlight is the difference between a local and a global coordinate system. Saya rasa you quite familiar with the local and global coordinate system for our previous lesson, right? So the thing is just similar, right? So the difference is just how we formulate the stress, what we call the stress element stress matrix to get the value of K. So that's the difference between the previous lessons, right? So we assume that we have our two-dimensional truss element. So we have one node and two nodes, and this is one element. So in the local numbering scheme, the two nodes of the element are numbered of 1 and 2, as I mentioned before, and the local coordinate system consists of the x prime axis, right? X bar, and we call x prime, right? X prime exists here, right? So the global coordinate system is shown in figures 4.3, that is has been mentioned here. So from here you can see that the global XY coordinate system is fixed and does not depend on the orientation of the element. Note that X, Y, and Z form a right-handed coordinate system. And then in the global coordinate system, every node have a 2 degree of freedom that I mentioned it before. So this is how it looks like for the global one. Okay, so from here, we have our degree of freedom of Q1, Q2, and then Q3 and Q4. So from here, the Q is mentions of the Q bar 1 here is represent the local displacement, right? So the local displacement for this one is calculated by Q1 cos theta plus Q2 sin theta, right? this is your Q1 and this is your Q2 for the node number 1. And same happen to the at the node 2. Your local displacement for the node 2 is equal to the Q3 plus cos theta plus Q4 sin theta. Okay, Q4 sin theta. Okay, so a systematic numbering scheme is adopted here. A node whose global node number is j associated with the degree of freedom 2j minus 1 and 2j. Okay, ini adalah bermaksudnya macam ini. Okay, when you look at the previous picture, so from here, so for example, if you refer for node number 1, so when here node number 1, it means that your first degree of freedom is here is 2 times by 1 minus 1 is 1. So that is how it explained to you. So same goes to the second degree of freedom for the node 1, which is Q2j, which means that when node 1 is 1, node your referring nodes is number 1, so j is node 1, so you will refer to the Q2. So it's a very understanding for you guys lah. So this is what they are talking about. So let Q1 prime and Q2 prime be a displacement of node 1 and node 2 in the local coordinate system. Thus, the element displacement vector in the local coordinate system is denoted like this, right? By refer to this form, okay? This idea, right? So the Q1 is the Q prime is equal to the Q1 prime, Q2 prime transpose. This is for node number 1 and this is for node number 2. So the element displacement vector in the global, so from the local you form into the global one, so you will get your Q is equal to Q1, Q2, Q3, Q4 as been mentioned before, because you have your degree of freedom of 4, right? Because you have your 2 nodes, right? So referring to the figures 4.3, the relationship between Q1 prime and Q2 prime as follow here. Okay, as I explained to before this one. Okay, so this is thing that, okay, so in the matrix form as Q prime is equal to LQ. Okay, Q prime, this is your local, is equal to LQ global, right? When L is the transformation matrix, right? So this is how they calculated for the L, which is the representing of the L, M, and also the LE, right? So what is L, what is M, and what is the LE? So this is how they calculated. For example, looks like the Pythagoras theorem, right? So if you still remember, so you have your x1, y1, x2, y2. This is your bar. This is node 1. This is node 2. So for example, if you want to find the L here, right? L is equal to cos theta, which is the x2 over minus x1 over LE. However, for the M, okay, is equal to the inverse of the inverse of the L, which is the sin theta, which is mean that's the M is equal to the y2 of minus y1 over LE. So what is the LE? LE is the what you call the length between 1 and 2, right? So how you want to calculate that, which is x2 minus x1 square root plus y2 minus y1 square root and square root all of that. So that is representing of your LE. Okay, I think that's very straightforward for you guys. So now we go for the another subsection, which is for how we want to calculate for the element stiffness matrix. I understand that I hope you still remember about the element stiffness matrix, how you want to calculate that for a 2D, right? So for the trusses, the calculation, it looks like different, but the method is similar, right? So for elements in the matrix, K prime for the truss element in the local, right, is given by E A over L times by matrix form of 1, -1, -1, and 1. When A is the cross-sectional area and E a Young modulus. It's very straightforward one, right? So when we want to change from the local to the global, it's become like this, right? When elements in the matrix is equal to AE times by EE divided by LE, and this form of the matrix, right, which is involved of the L and also the M, where you get this number from the formula here. Okay, if you still remember, for the every bar. Okay, so that's all for that, and then that's all how to calculate for the element stiffness matrix. So now you go to your stress calculation. So it's similar with the previous lesson. So from that, if you want to find a stress, is equal to E times by strain, right? Do you still remember your E is Young modulus is equal to stress over strain, right? So you move to the strain in the up, so you will get the stress straightforward is equal to E Young modulus times by strain. Since the strain is the change in the length per unit original length, so you what we call you substitute the value for the strain here with the another formula, so you will get a Q2 prime minus Q1 prime over LE, which is the formula for the strain. So from that, you improvise this kind of formula, then you will get these things. So this equation can be written in terms of global displacement Q using the transformation Q prime equal to LQ. Okay, this is I said to you before. So from that, you improvise on that, you improve the formula, so we'll get the stress is equal to EI over LE, a matrix form of -1 or times by LQ, when L, as I mentioned before, is the formula of that. So from that, you improvise this formula. L you substitute here, so you times 1 by 2 times 2 by 1, so you will get times 2 by 4, so you will get 1 times 4 matrix. So from that, this is the final one where you want to calculate for the stress in trusses, E over LE times by negative L, negative M, L M times by Q. Okay, that's very straightforward one. Okay, okay, now we want to go to the example of that. So that's only lesson for trusses. I think you must to try the example. We will go through together for the example. Okay. Okay, for example, consider the 4-bar trusses shown in figures 4.5 below. So this is your problem. So you have your 1, 2, 3, 4 bar. Okay, correct. So figure 4.5 is given to you your E and also your area, cross-sectional area for all elements. So first of all, you need to understand the first question is determine the element stiffness matrix for each element. So for that, you need to find your K1, K2, K3 and K4, and then assembly the structure. So have been practiced from a previous lesson, how you want to become local to become a global, right? So we need to combine the matrix following the numbers of the degree of freedom. So we need to combine it, become a big matrix, and then C, using the elimination approach, solve for the nodal displacement, how you want to calculate for the Q, and then the D, recover the stress in each element. You need to find the stress, and then you need to find the forces, which is R. Okay, so from back to our problem. So this is given to you. So from that, for every node, they have your degree of freedom for each node. So you Q1, Q2, Q3, Q4, Q5, Q6, Q7 and Q8, and then you have your element 1, element 2, element 3 and element 4. It's a very straightforward, and of course you have your axial load, your axial force acting on node number 2 and acting on node number 3. So this is how they are given to you for the to solve the problem. Okay, so what do you need to do first is you need to understand the nodal coordinate number. You need to represent your nodal coordinate data and the element information. So you need to find the distance or the length of the bar. Okay, so for example, we go through one by one. So for the node 1 is 0 0, so it means that you assumes that the node 1 is your origin, starting point of your length. Okay, so this is your origin, so it means that your node 1 is equal to 0 to 0. That's fine. For the node 2 is 40 0. In order to solve the problem, you need to make sure your dimension is consistent. It's up to you, either you want to use the SI unit or not, but you must be consistent in order to get the same answer with the scheme. Okay, and then for the node number 3, you will get 40 and 30, and 4 is 0 and 30. This is very clear, right? So the element connectivity table is same as a previous lesson. So the element 1 is connected between 1 and 2 nodes, okay, and then 2 and 3 and 4 element is similar one. So, and then this is the notice that you need to remember, that for the connectivity of element 2 can be defined by 2 3 instead of 3 2. It's up to you. If you want to start from 2 to 1 or 1 to 2, it's up to you. You will get the same results. Okay, and then for that, using the formula in figures 4.4, if you still remember the figure of the Pythagoras theorems, right, together with the nodal coordinate data and the elements and the given element connectivity information, we obtain the direction of the consign table like this. So you know how to calculate for the LE, you know how to calculate for L and M, so you will get the result for every element. Okay, okay, this is they given to you the example of that if you forget about that. Okay, okay, so and then we continue. So the first equation, the first question that you still remember is he asking you about the stiffness matrix for every element. So from that, this is very straightforward. If you still remember our formula for the stiffness matrix, this one, this one, okay, you implement all these things and then calculate, substitute the value of L and M, you will get your stiffness matrix for the element number 1 is this, element 2 is this, and element 3 is this, and element 4 is this, right? I recommend you to try by your own, and then you will get the same result or not, right? This is a very good practice for you in order to find, or in order to you to solve the problem from our final exam. So it will help you more on that. Okay, so for the second question, it's asking you how you want to combine for all the global stiffness matrix. From here you have your element 1, element 2, element 3, element 4. You need to compile for everything. I think you're familiar on that, so I'm not worried about that. So for example, for the K1, I just make a quick revision on that. If you are not remember on that. So for K1 is related between degree of freedom of 1, 2, 3, 4, 1, 2, 3, 4. So this one Q2 is similar, is related with the 5, 6, 3, 4 and 5, 6, 3, 4. So this is your number of degree of freedom. For when you want to combine for your global stiffness matrix, you need to refer all the numbers here. If their number is similar, you just make it plus. Okay, and then you can try it and you will get this this number, this form of matrix. I hope the numbers here is correct, but if wrong is okay, it doesn't matter, because I think the numbers here and also the numbers from my books is quite different, but you can try, right? So you can check either this number is correct or not. Okay, and then we continue for the question numbers. Question number 3, which is number C. They're asking you about the global displacement, right? They're asking you how you want to calculate for the displacement by implement the elimination approach. If you still remember from our previous problem, the fixed one will be Q1, Q3, Q4, Q7 and Q8 is equal to 0. So you can use the elimination method, and then you can solve to find the Q3, Q5 and Q6, and this is how they are they are calculated for you. So you have your Q3, Q5, Q6. I think you are quite familiar on that. So you have your F here. So KQ is equal to F. So you make the inverse of the elimination method. So you will get your Q straightforward here. From here you need to try, and then you will get the same result from here or not, right? So from that you rearrange again. So you will get the nodal displacement vector for the entire structure can be written as this one, right? So 0 0 here because it's fixed, right? So continue for the next question. Is about stress. So this is what you need to implement for that. So because you have your 4 elements, so you need to find for every element they got every kind of stress. So from that you need to calculate for the you substitute all this thing here, all the value of the L, M, and also the Q there. So from that the stress value is written by this one, Q through for the stress 2, stress 3, and stress 4, right? This is a very straightforward one, right? So, and the last one, they're asking you about the reaction force acting on the bar. So means that the main concerns for your solution is, okay, you have your reaction force for the Q1, Q3, and then Q4, and also Q7 and Q8. So you have a 5 point that you need to find, right? So this is given to you, Q1, Q3, sorry, not Q, R1, R2, R4, R7, and R8, right? So you fill it, you mix and match on that. So in order to what I call untuk mempercepatkan hasil solusi anda, hanya concentrate pada value yang kita perlu cari. Okay, you can find for every external force acting here, R1, R2, R3, R4, R5, R6 semua. Tapi you will get the R3 must be equal to 0 and on that, right? So if you want to be a quick solution during the final exam, you need just concentrate on what we want to find, and then from that you just cut it off. Because do you still remember our global stiffness matrix have 8 and 8, right? So just cut off what we don't want to calculate. For example, so we just need R1, R2, R4, R7, and R8. So you just take R1, R2, R4, R7, and R8, and that is what they are mentioned here. Alright, so this is 5 by x times by 8 by 1, so you will get 5 by 1. So this is very straightforward mathematics. So we'll get the result for the external force acting on the bar is equal to this one. I prefer for you to try, and then you will get the same results on that or not. Okay, don't worry about your final, because the finals exam, the finals question is looks like a similar that what we discussed here, right? So you before you going to your final exam, you need to try, and then you need to understand what the how the flow of the solutions until we get the final answer. Okay, this is the free body diagram from previous one. Okay, I think that's all for topic 4, which is trusses. The temperature effect will not be covered from your level. Okay, we at the problem before. So that's all for chapter 4, trusses, for your subject. So if you have any problem or any questions, you can direct call me or direct WhatsApp me from my number 013-6261-363, or email to me mioikram@ukm.edu.my. So we can discuss, we can talk, or we can do together the problem that you not understand. Okay, I think that's all from me. We have quiz after this, but I think I will do a quiz for a next chapter, not for this chapter. Okay, so see you guys. Assalamualaikum and terima kasih.